Yes. So Jason just said this. I've submitted this talk to CPPCon. Only John knows at the moment in this meetup whether it will be accepted. We will see. If it isn't accepted, then you're seeing perhaps the only version that will ever go out. Do please ask questions as we go. Just break in. I don't have the chat visible, but I will. Let's see. I will bring up the chat.
I'll also let you know if you're missing anything.
Yeah. Oh, thanks, Jason. I'll try to look at the chat from from time to time. Do please ask as we go along, and let's get into it. So, deducing this is a paper, P0847. It's a paper by myself and Gashper, Sai, and Barry. And the abstract in brief says, we propose a new mechanism for specifying or deducing the value category of the expression that a member function is invoked on. In other words, a way to tell from within a member function whether the expression is invoked on, i.e. the object that the member function is on, is an L value or an R value, whether it's constant or volatile, and its type. Okay, so please ask questions as we go. We're going to talk about, I'll start out with a bit about the history and the motivation for this paper, and then we'll get on to what it actually is and what it isn't, and some existing patterns that will become sort of evolved and better, some new stuff that the paper makes possible, and some miscellany at the end. One of the, what was I going to say? Okay. Firstly, let's talk about this kind of an origin story. So around about middle of 2013, I started playing around with monadic futures and trying to write sort of library. And I ran into a problem. And then in 2014, in May, that was the first time I went to C++ now. Met John, I think, met Lenny, met a couple other people. But was totally overwhelmed. So kind of attended as a new attendee. May 2015, I went back, and at that point I felt able to talk a little bit more about this problem that I had on my mind with folks. So that happened. 2017, that happened, and I came home and just sort of, that was that. 2017, I talked to Gashper at CPPCon, and he got really interested in solving this problem. He and I were talking about it that year at CPPCon. A bit later on in the year, we learned that Sai and Barry were working on the same idea, and we all joined forces, and we made this paper. And then in May 2018, Gashper gave a talk about the paper. Now, you can look up that talk. It's at C++ now, which means it was brilliant if you were in the room, but perhaps it's not so accessible if you watch it on YouTube later. Really, you know, the feature is now, the feature was presented for the first time in June 2018 following that talk. So that talk is also very much kind of pitched at the people in the room who were some of the people in the committee. And it's like in many C++ now talks that you see on YouTube, there's a lot of questions in the room. So here we are, fast forward late summer 2021. The paper's at revision 7, and it looks to be pretty baked at this point and heading for standardization, hopefully in C++ 23. So in this talk, I want to sort of explain the feature more in a rewatch friendly way, now that it's kind of almost fully baked. So here is the problem I started with. I was playing with monadic futures. I was, you know, working in a code base where we're using callbacks. I was playing with this way of executing callbacks, and I ran into a problem similar to this. So you have a callback, and you have a value that you move into the callback, and you pass that callback off to some asynchronous operation, and then later on it gets called back. Now, if you want to be optimal, you want to know whether or not you can move value when you call that function. But it's difficult to know sometimes, like it might be a one-shot callback, in which case you're just one and done and you find you can move it, or it might be a callback that the machinery holds onto and calls you several times. In that case, you can't move it, perhaps, or until perhaps it's the last time, right? So the caller of the callback knows the last call. And so it can sort of cast you to an R value at that point, or at least cast the call back to an R value. But inside the Lambda here, there is no way to tell whether the Lambda, the closure object itself is an R value. So there is no way currently to tell this. And so there is no way to properly be safe in all cases here and be optimal in all cases, perhaps. So this was one variant of the problem that I ran into. So time passes. Like I said, I went to May 2015, and at that time I felt able to talk to people, but their response was pretty much, well, you know, we have bigger fish to fry right now. We know this is a problem, but, and this was fine because it was just after C++ 14. And if you remember back then, everyone was looking forward to C++ 17 and expecting it to contain all these massive features. There were lots of high hopes. C++ 14 was kind of labeled the small release after 11, kind of bug fixes. In retrospect, it actually has some pretty cool things like generalized constant expr, deduced return types, generic lambdas, init capture. You know, these are all kind of large, but if you remember back then, it was kind of like this TikTok release cycle that people thought C++ was following. Anyway, so that was why I didn't get a lot of traction then. You know, and this timeline kind of shows you the sort of time it takes perhaps to get things into the standard, looking back, you know, from sort of first recognizing the problem and sort of then working it a few years and formulating what it should look like in C++. Anyway, so I pick up again in late 2017. Gashper and I started talking seriously about how we might solve the problem. And we start to realize just how many applications this might have. So like I said, in 2018, Gashper gave this talk at C++ Now, and that talk was very much for the people in the room who were several standards people, in particular, several standards folks who sit on core, that's the language side of things, rather than the library side of things. Because this was sort of an interesting insight into the committee that I had at the time. You know, we talked to lots of folks. Universally, the library side folks just were like, I can use this, give me this feature now. I want it now. Like I can go and delete thousands of lines of code, et cetera, et cetera. And the language folks on core, they were like, well, not really sure I see the use case, you know, I'm not sure about this. And, you know, this is a kind of a glib way to put it, but this, in the sense, this is kind of how the language should work, right? It's kind of, library is, you know, described by some people as like Wild West compared to core, which is like, apparently, I've never been there, but apparently it's a room where people sit in silence thinking very hard. And, you know, introducing new features to a language, you want to be sure that they play nicely with all the other features. And you have to kind of think about all that combinatorial interaction with all the other language features. And there are, as we'll see, some very esoteric corner cases that standardization has to consider. However, the feature itself, okay. This slide really is the entire feature in terms of actual language additions, or at least if you write this with this feature, by the end of this talk, my hope is that you will understand this completely and its implications. And one of the best things about this feature is that it doesn't introduce new magic. Like there are lots of things in our language that are magic already. And this is not one of them. It's a relatively small addition with large implications in terms of the way it interacts with existing language features and in terms of the way that you already understand how C++ works, right? So we will just spend this talk basically considering how this works and following through the logical implications of interactions with the language. I should say by convention, we use the identifier self here, just that's kind of conventional. And as we go along, you'll see what that means. So what changed and what didn't? Basically, as you see in the previous slide, on this slide, the this keyword here is a new annotation on the first argument, on the first parameter to the member function. And it makes the sort of implicit first argument, which is the object that we think of generally, and indeed is explicit in some languages like Python. In C++, it takes that implicit first argument and makes it explicit on non-static member functions. And that's all. By design in this feature, almost everything else is unchanged. No change to template deduction rules, no change to overload resolution, a very small change to name lookup, which makes sense in context. This is still a pointer. You can be sad about that. You know, C++ had this before it had references. So this can never be null, and yet it is still a pointer, not a reference. That is unchanged with this. And the meaning of this inside the Lambda is also unchanged. And this is kind of important, the things that didn't change in standardization, because if we had tried to change any of these things, firstly, it would have been much more complicated. Secondly, it would have received a lot more people against it, right? Like you try and change any of these things, you run into like breaking lots of code, basically. Okay, so the good news about this feature is that you already know as C++ engineers how this is going to work. When I tell you these things, you will already be able to take what you know about C++, the regular rules, and just apply them and follow them through to their logical consequences.
So Ben, we do have a couple of questions in the chat window, yes, just to make sure. Chris asked if concepts can be used with it, and Daryl asked if it works with assignment as well.
Concepts can absolutely be used. Well, I'll have some slides later about that. I assume you mean, does it work with the assignment operator equals? And the answer there is yes as well. It works with operators. Okay, hopefully that answered both questions. So yes, we're going to spend the talk sort of following through these consequences, but the basic rule is, if there's like you apply the rules of C++ that you expect, and that's how the feature probably works. And good news for trainers, it's probably very teachable, because it's how other languages tend to work. It's how our mental model works. And as I said, it works in concert with the existing rules. There's no magic, there's no extra magic here. Okay, so really quick sort of first slide. This is kind of how things look today. This is one example of the feature in action. This is how things look today. This is how they can look with this feature. And this actually isn't doing any deduction at this point. This is just showing that you can use it in sort of regular mode without templates. And it's just an alternative way to write these value category reference qualifiers and value category sort of qualifiers. So the top of this slide and the bottom of this slide represent identical declarations. They're both still valid with this feature, but defining sort of both at once will be a double declaration. So don't do that. They are literally the same thing.
Okay, so I have a question. If looking at the bottom one, the middle one, this S reference, it looks like we can't do the non-reference qualified. Like this specifically is implementing the reference qualified, not the what it would default.
Oh, so just auto func with no reference qualifier?
Right. What would that do?
I don't think you would want to express that in this way. So I should amend what I said before. These are the same function on the object, but there are a few differences we'll get to later. But yeah, auto func with no reference qualifier it does have no equivalent in the new syntax, I think. Right. So let's have a look at some things this gives us. So this, as I said, is exactly the same, and we're not doing any deduction here. We're just doing the regular kind of overloads that you would provide with the reference qualifiers. Now, the first obvious win that we get with deduction is a huge amount of deduplication. And this was kind of like the first thing that everyone, all the library people we said immediately, recognized this fact. Because, we commonly write the top two things here. We may write the third one. We seldom write any others, but you know what they all are, like const R value refs, and if you want volatile as well, Jason would throw in, and all that extra stuff. So instead of this, going back to what you saw before, this will replace it, right? So the compiler will deduce the type of, it will deduce self here. The implicit first argument becomes explicit. So this function declaration, if you call it on an R value S, then it will come through as an R value. If you call it on a const L value, it'll be a const L value. The compiler will synthesize all the overloads you use, right? At the point of use, the template gets instantiated. The compiler synthesizes it perfectly. So that's the first kind of obvious thing that we get. And this already is a big deal, because right now you kind of have several choices to provide these overloads, and none of them are particularly palatable. What you probably do, what I do, what we all do is you just leave out some of the overloads. But your other choices are, write them all separately and duplicate the code, or delegate them to a particular one. I think there's in one of Scott Meyer's books, there's an example of doing that. You have to kind of const cast from the non-const version to go to the const version or something like that. Or you can choose to delegate them all to a template helper function, right? They all require some kind of copy pasting, right? You have to actually write the signatures today, and that is required. And anytime you get copy paste, you introduce room for error, right? So all of those functions, if it's just like a getter, you get them all with this recipe, right? And we can do a single optimal, sorry, I've got a question in the chat. The following is valid. Yes, Chris, that's right. We'll come to slides later, but anywhere you can put a template, for example, here, type name self could read concept self. And likewise, you could say this auto ref or this concept auto ref.
Also,
in Chris's example in the chat, actually, this has to be first. This specifier comes first. But after that, you get the auto ref or the concept auto ref.
Do you want decal type auto on this slide for that to be actually correct, Ben?
So, okay. So this is where I have the see next slide. So what should the return type of this be is the question. I think Lenny's about to paste something in the chat. Good, we're getting lots of questions. This is great. I'll Lenny, go ahead and ask the question or whatever. I'll continue a little bit. Auto func this like auto, because the way you would normally specify a concept would be to include the auto keyword there. But yes, that's correct. With this annotation always comes first. Yeah, so Jason brought up what's the return type of this? So if you want kind of sort of perfect forwarding, yeah, that's exactly right, Lenny, in the chat. You need to have this little recipe, perhaps, right? If you want kind of perfect forwarding and value wrapping. And that's why, so mentioned in the paper, although not proposed for standardization, are a couple of little meta functions that I'll mention in this talk. Like t is this meta function that takes it applies the value category and const qualifiers, it sets CV qualifiers from its first argument to its second argument. And you know, this is a meta function recipe that you can probably already find online. Not too difficult if you're an experienced meta programmer to write this function. Basically, you can assume the existence of this, and this is a recipe for spelling the result type of a function like a getter, where you want the sort of perfect forwarding out of the object. So this recipe gives us the ability to write a sort of optimal single template method for a getter in this case, and it immediately replaces the quadruplicate, you know, const ref, mutable ref, r value ref, and const r value ref. And if you care to write the volatile things, then it replaces those two. Okay, so I think at this stage, hopefully everyone understands the kind of first obvious use case here. And are there any further questions about this particular thing? Okay, great. So there's like t, there's also forward like. And forward like does the same thing as forward, except it applies all the stuff from t onto u, right? So forward to u like a t. And these two are generally useful in writing wrappers, things like optional value wrappers, as we saw, getters. Okay, so those couple of recipes, fine. Okay, so that was the first obvious win. This slide explains a little bit more about, you know, like template deduction works the same way it works now. It works the same way you would expect. They work like normal. And this becomes kind of important, the deduction will deduce the most derived static type with its CV ref qualifiers and value category. And this fact, you know, the fact that template deduction is unchanged. So in the second case here, derived is a base, right? Because it derives from it. And func2 is a member function of base, as indeed func1 is. So when you call func1 on a derived, you're not deducing, you're just sort of writing this in the new syntax, right? So you're going to get self is a const base ref. But when you call func2 on a derived thing, it will deduce the static type that's most derived, because D is a derived, self will be a derived ref. And so you get type derived ref, mutable derived ref, right? And this is kind of exactly what you do. If these were free functions, this is exactly the same. But this fact that template deduction deduces the most derived type, the most derived static type, becomes really important to consider kind of how this feature plays into C++ and how it leverages existing features and how powerful it is. This turned out to be very powerful. So consider what we know today as CRTP, the curiously recurring template pattern. And this is a way to statically mix in functionality from usually fairly small base classes. And it's a way to get this kind of static polymorphism without incurring virtual methods. And if you use it today, it looks something like this. And there's this very sort of conventional pattern involving the static cast, right? So sensitivity, it's curiously recurring, right? Because we pass itself into its base, numerical functions here. And then here's the static cast inside the scale function. This is the way, this is just the pattern that CRTP uses, right? This is the way CRTP is done. It's a downcast, but it's safe because we know that the thing that's calling this is we know that you know, it's a t, and so we cast it to a tref, and then we call set value, right? This is the pattern of CRTP today, and it's used, I'm sure many of you know, to provide things like mixin operations that work in terms of a class's basic interface. So if your basic interface here is sort of get value and set value, the mixin, you know, provides value, provides functions that work in terms of that basic interface. This example, by the way, is from Jonathan Bacara's blog, fluentcpp.com. If you haven't seen it before, it's well worth going and looking at not just this, but all of his articles. So let's consider how CRTP changes with P0847. And it looks like this. The classes aren't templates anymore. The classes are just types. There's no recursion, there's no class template, because the function is a template that can deduce the type of this point of the object. And so it can use it directly. When you call scale on a sensitivity, self is a sensitivity, right? Because deduction will deduce the most derived type that's statically available. And so the mixin is just flat, as it were. And this works. I should say that this feature, as part of sort of working it towards standardization, has been implemented by Gashper working with David van der Voorde on the EDG compiler, I believe. And you know, so basically, it's been shown to work. That's often something that happens during the standardization process. So a few things in the chat. A numerical function's reference or pointer would act like a virtual function. Well, the call to scale acts like a virtual function. CRTP's job, in a sense, is to provide the same kind of patterns as virtual functions, but statically, right? So the CRTP pattern allows you to call scale as if it were a virtual function, because it's going to work in terms of the most derived type. But with P0847, with deducing this, when we call scale on a sensitivity, it deduces to a sensitivity. And so we get this without any of that nonsense about static casting or deriving and recurring. It's just, there's no curious recursion, there's no template. There's just the pattern. Comment says, but now it's the same pointer or ref for multiple types. The name is not the same in CRTP. Not sure I follow. If you want to speak up.
Might be easier if I say, so like with the virtual class, you can use the same pointer to refer to different base class or child classes. You could do that here. You got to worry about destruction, but you're getting almost the same benefit as a virtual class here with virtual functions, but you now have the exact same name that they're in ISA. Whereas before you'd have numerical functions and with a template parameter sensitivity, so you'd never refer that, you couldn't have a common pointer to them.
Right. I think I see what you're saying. That the base was a template before and it's not now. So you can't have a pointer to a template, but you can now have.
Well, you can if you said numerical functions, you know, alligator sensitivity, but it's that's really cool. Sorry.
Wait, so go to the next slide though, because I want to.
Okay. Well, wait, the next slide after this.
No, this
the previous slide?
This slide. Sorry. Any of the one with the deducing this version. Sorry. Yeah. So if I passed a reference to a numerical functions to a function and wanted to call scale on there, there's no way that it could know that it's a sensitivity inside that function.
Correct. Yeah. No, you're going to get static typing. If you pass around, just the same way that in this slide, d.func1, it's a const base ref in that function, right? You're only going to get what the rules of static typing say.
Oh,
Around
so it's just going to blow up
functions. It's not going to do like a virtual call. Right?
Okay, so it's going to blow up.
Oh yeah, it would fail to compile if you tried to call it via reference to numerical
it's going to
functions.
fail to compile because there is no set value in numerical functions.
Okay.
Yeah.
Well, I'm less excited, but it's still cool.
Well, okay, cool. We're still in kind of early applications here. Maybe you'll get more excited as I talk further. Okay, so CRTP kind of sets the stage for kind of consider a builder pattern. So a builder pattern today would look something like this. You know, you want to use this kind of, it's sometimes called fluent style, where you chain these function calls together. But the basic idea is that the methods return a reference to the thing so that you can keep chaining the function calls. And this is a common pattern in some styles. So the question arises, you have a builder. What if you want to make a specialized builder that knows how to do extra stuff? Well, this is where it gets a little bit hairy. CRTP comes into play. You have to do something like this, right? So the special builder derives from builder of special. There's the CRTP. C and D will return special refs. But now, in order to make, you know, calling A, if you look at right at the bottom, we say special.a.c. That means that if it's a special, A has to return a special ref in order to call C, right? Not just a builder ref. So we have to kind of do this dance where we figure out the derived type to return. And you know, this is ugly and horrible and error prone. And it gets even worse the deeper you go. If you want like a super special builder, then I mean, you can do it, but it's just metaprogramming. You know, there's a lot of metaprogramming here. So you can get like this is C++, so you can always do almost anything, right? But it's super ugly. It's super not nice and error prone. And you know, I don't know about you, but if you've done any template programming as I have, one of the really hard things is, you know, figuring out why you got way down deep in a template, why you got a const ref rather than a ref or whatever. Anyway, that's what it looks like today if you try and do the builder pattern, and it's sort of it's an application of CRTP. But with P0847, it looks like this. Like there's no problem. It's just a flat pattern. It's all the same. Because no matter what level you call this at, self is going to be deduced to the derived type. So you will automatically return the derived type reference because that's what self is. I see Jason with his head sideways looking at this slide.
Well, yes, because I'm thinking about the last slide and I'm thinking, well, if I passed a generic builder reference into something and try to call C or whatever, then it's not going to compile. If I call A, then it's going to deduce the base builder, not the derived builder that I thought that I passed into it.
Right. So the same thing as we said a minute ago. This is using templates, right? So in a sense, this is all about static typing. Like you are not going to get virtual functions. By the way, these functions cannot be virtual at the moment. This is doing the same job as virtual functions, but in the static type space. The CRTP, that's what CRTP does, right? And so that's what this application of P0847 does. Okay, so the improvements we've seen so far. First of all, more functionality for less code. Like that one getter replaces 3, maybe 4 getters. The compiler synthesizes it for exactly the right types that you need. You get that, and because of that, you get sort of more comprehensive coverage, right? You don't, right now, if you provide const ref and mutable ref, and you call it with an R value, it's gonna take the const ref overload, but if you had an R value overload, that would be kind of more perfect. And with CRTP, you don't get this kind of explosion of complexity. You don't get this complicated implementation of passing types through to their bases and all that sort of thing. So all these are great features, but they aren't actually new. Like you can do this with C++ today. It's nice that PO847 makes it easier. And it helps you stay a bit sane. But PO847 does more, because when we start to think about this, we start to see things which are not possible today in C++, and PO847 makes them not just possible, but easy. And one of these things is, so if we're deducing the type of the object, why can't we deduce it as a value and not a reference? It doesn't have to be a reference. It can be by value. And, if you just think about this for a second, again, you know how this works. This is regular pass by value. Less than here is an empty object. And this is actually better than we have today as well, because, less than is an empty object. It's analogous to a non-capturing lambda, right? They're empty objects too. As it is today, C++ is required to make and pass an implicit this for the less than object, and indeed for any non-capturing lambda, right? It has to make a reference, allocate a register for that reference probably, and maybe somewhere way down the line, I'm not even sure the optimizer is allowed to optimize it away, but basically here you pass it by value. The optimizer will totally optimize it away because it's literally empty. Copying it is free. There is nothing to do. So PO847 kind of unlocks an optimization here. Yes, Jason said there is a proposal for a static operator paren on non-capturing lambdas, I think is what you mean, Jason, yeah? In the last mailing.
Not just on non-capturing lambdas, I think generally to be allowed.
Okay, yeah, that's Barry's proposal. It does, yeah, this particular use case is one of the use cases that a static operator paren would improve. There are other use cases for static operator paren. I think this particular one is better improved by PO847. So yeah, here we are passing the object by value. And somebody asked earlier, was it applicable to operators? Here is an example of that, the operator paren. Here we're passing the object by value, we're taking it by value, and everything we know about by value functions applies here. It's just regular pass by value. So we actively want to pass small or empty types by value. Types that will fit in the register, you want to pass them by value because if they're empty, the optimizer is just going to say bye-bye, don't need that. But before and we can do this with free functions, but we cannot do it with member functions, right? Before PO847. And just like I was saying, the result is we're just leaving perf on the table. String views are a small thing. Now, I should say this, we can dream about this, but, ABI breaks mean that we'll actually never get this probably. But, small things like string view, we can imagine that they take their objects by value. And, that's sort of a free optimization. Chris asked, would you make that function const too? Yes, yeah, there might be some const that I left out of this slide. Yes, you could totally You could say this const basic string view self, or indeed this basic string view const if you're east const. I might have left a const or two out of this slide, and the function itself need not be const qualified, because it would be the same as writing this const basic string view.
Would that even compile if you tried to put a qualifier on that function?
That I'm not sure about. That's something for like a language lawyer to answer. To be honest, I'm not sure if I don't know if the grammar might allow it. I'm not sure is the answer. So, you know, this is kind of like passing small objects or empty objects by value to their member functions is sort of a free and easy optimization that we can get with P0847. And kind of the more extended version of this is that in general, we can pass things by value. And sometimes we could do that to move values through computations with kind of the builder pattern. So if we wanted to get a sorted vector in this case, this is sort of a trivial example. And here, of course, the compiler is required to move things into the argument and to move things out of the return statement. You know, it's mandated to move. And so what we get here is the move all the way through the computation chain. And we can do this today with free functions, but we can't do it with member functions precisely because the compiler is required to have a reference to the object to call a member function. So with P0847, we get this in member functions as well. And like I said, move is mandated on return and into arguments. The compiler will just move. Any questions at this point? Jason shaking his head. Chris said outer const is decayed from arguments normally. So if this is by value, I guess a const qualified function may have the const just dropped. Yeah, I think you're probably right there. Const on parameters is generally more for signaling how you use them than for anything to the compiler, I think. To people, I mean, signaling to people. Okay. One of the other things that we get from by value functions is lifetime management. If you think about a coroutine, this is analogous to like why we have range 4 in it, right? And it's not always obvious where you need it. So if we make a coroutine generator C, and then we call .always, the temporary C that we made falls out of scope, and we have dangling. We have a dangling thing, right? This is range 4 initializer is exactly kind of to solve this problem. If you know range 4 initializer, but it's really kind of hairy to know where you need it, where you don't. What we can do here is make the always function take a C by value, right? And when we do that, there is no lifetime problem, because by taking it by value, it's now not dangling inside the coroutine. We took it by value, so it lives by value inside the coroutine, as it were. Inside that function, there is a C, and we're co-yielding its value every time. There's no dangling after we return from always, because it's effectively suspended. Is that clear? Any questions? Maybe people aren't really used to coroutines. There may be other things I might think of for examples, but this is one from the paper, and this kind of the by value, the dangling thing of range 4 in it is pretty much a sharp edge in C++ today. Anyway, so there's nothing special here. This is regular pass by value. We just kind of have to reason through the implications of how it interacts with deduce this. And what we get is great. We get better performance for small objects that you can pass in registers or that are completely empty. Compiler doesn't need to form a reference and pass it anymore. We get this new ability to move values through chains of computations without templates, without free functions, with regular member functions, and new lifetime safety options, because we can take by value, we get a copy of the object or the moved object inside the function. So this now leads me back to the original problem, and now we can see how it's solved. And this slide also kind of demonstrates like one of the reasons we chose this particular form of the syntax. One of the questions most commonly asked to myself and the other authors of the paper is, did you consider such and such a syntax? Like in particular, this looks weird because I'm used to putting ref qualifiers at the end. Did you consider such and such syntax? And the answer is always, yes, this syntax was actually really carefully considered in consultation with a bunch of folks in the committee, and we settled on this. And one of the reasons is that it's consistent with the Lambda expression usage. So this is a regular Lambda, except that we can deduce the this. But now that, because it's a Lambda expression, the this that gets deduced is the closure objects type, right? Which previously, like today in C++, this is not possible. You cannot, inside a Lambda, know the type of the closure object. But now you can with P0847. Yeah, Jason says in the comments, explicitly disallowed. We'll get, Lambdas are special. We'll get to talking a bit more about them soon. But now this already solves my original problem. Okay, so there's more. Let's talk a bit about how to write Spina-friendly callables. And here's where a bit of code comes in and a few templates. Apologies for that. How you write, like this is kind of like the standard library function not fun, or an example, a kind of an expression of it. How would you write this today? Well, it might look something like this. And here we have two overloads of operator paren, one for mutable ref and one for const ref. And, I left out all the others. And you do something like this, right? Ignore the trailing return type business. That's kind of just not that relevant. But you return a not wrapper from not fun. You return a not wrapper of decay T of F and you forward the F into it. Okay, fine. Well, I say fine, but then you come up against like badly behaved F, right? Somebody might write a callable that's Spina unfriendly, right? It has a non-const overload and a const overload, and they have static asserts inside them, right? When you try and call this, even though the compiler knows which one to call, it has to instantiate both of them, and you hit a static assert and your compiler goes boom, right? Even though it's clear that you want to call the int overload, or that actually the overload dictated by the argument, it's clear to a human, but the compiler has to instantiate these things to figure it out, and you hit the static assert and Spina doesn't happen. Your compilation just stops. There are lots of Spina unfriendly things in the standard library today, as you'll know if you've tried to do anything moderately involved with metaprogramming. This is a common problem. Another kind of callable we might try is like, we're trying to be safe, so we are deleting the non-const overload here, right? So we try to call it with 1, so we want it to be deleted, right? That's the best match, but it's not the one that we end up calling, just because of the way C++ works. These kind of problems are really, really difficult to solve in C++ today. And in some cases, we haven't actually figured out how to solve them yet. That's one of the reasons why the standard library is really kind of messy in this area. These problems are really hard. With P0847, they get much easier. This is a complete implementation of notfun with P0847. And I just put it in a Lambda because I could. Boost Hoff returns is just this macro that solves the you must type it 3 times problem. So basically, you need to say the trailing return type and the no except clause type and then the body of the function. And it's basically, you type this same expression out in triplicate for those 3 things. So Boost Hoff returns is just wrapping that. But this is what it looks like. You return a Lambda, you capture F by forwarding. And because you can deduce the type of the type and value category of the closure object, all you need to do is invoke F as if it were, forwarding it like the closure object, forwarding all the arguments to it. That's it with P0847. That's a complete solution for, what C++ today really can't solve. Some of these cases are not soluble, or at least not likely to be solved anytime soon. Okay, so that was, I appreciate a template heavy interlude. Does anyone have questions at this point? Silence. No, nothing in chat. Jason's typing something. No, okay. All right, well, let's move off of that. That's this kind of thing is, did I say P0874 and P0847? I always get these mixed up. Yes, okay, I typoed that. For the longest time, I couldn't remember the number of my own paper that I was a co-author on. Thank you, I will fix that up.
It's just because you have so many papers in flight right now, Ben.
Really not, but sure. Okay, so I should say that, while this may not apply directly to your code today, this kind of thing is the sort of thing that library people on the committee get super excited by. Okay, let's talk a bit more about Lambdas, because we all love Lambdas. We've loved Lambdas since C++ 11. So there are a few things I need to cover about how this paper works in Lambdas. In particular, I mentioned that the meaning of this is unchanged inside the Lambda. This proposal totally sort of solves the issue of how to write recursive Lambdas. And there's some really interesting things about deriving from Lambdas and making overload sets from Lambdas, and a couple of caveats. I will try to be careful in the language I use here. We often use the term Lambda loosely. There are 2 completely separate concepts. The Lambda expression, the thing that you write, it's an expression that gets evaluated by the compiler and produces the closure object, right? Which I've said a couple of times already. I'll try to keep to that kind of more specific language where we need to. So as I said, uniformity of syntax was one of the driving reasons why we settled on this particular form of the expression, and its uniformity between regular member functions and Lambda expressions. So here are a few things we did consider. Alternative 1 here makes this not a pointer, right? And that is right out for all sorts of people. That breaks things, that makes things really complicated. That was pretty much a non-starter. The proposal would have been dead. Number 2 here, we did consider also, but it turns out it has some parsing issues. And, one of the things I've learned through my admittedly not very deep interactions with the committee one of the things I've learned, though, is that C++ as a grammar is really complicated. And there are some things we can't do because the parsing gets really, really much gnarlier even than it is already. There are some places where there's just no room in the grammar to fit it in. Number 3 was considered. So number 1 was putting this as the mandated name of the parameter. Number 2 was adding a marker to the existing CVRef qualifier place, putting a self on the end or whatever. Number 3 was just adding a type marker to the existing place and using this as normal. This has issues with lambdas too, and possibly issues with dependent types. There's all kinds of esoterica that goes on with that, sort of how to consider that. But no, the proposal we settled on, what the syntax we settled on was one that worked with lambdas and member functions alike consistently. So, as I mentioned a couple of times though, now this inside a lambda expression still means what it always has. It means the this that you captured. It means the object that you're in outside the lambda, right? It doesn't mean the lambda's closure object. You obviously you get to name what we've been calling self. This remains a keyword, so you can't name it this. So there's no interaction there. There's no breakage. Of course, we can still be sad about this capture. In my opinion, it's a wart in C++. Basically, init capture solved everything, but we keep shoehorning in weird captures in lambdas like star this. I'm not sure why, but I recommend init capture. Okay. Recursive lambdas. I said recursive lambdas were solved. Here's a recursive lambda. Here's your standard recursive Fibonacci. And it takes its own closure object by value, you'll note, because this is an empty lambda, so why not? And this is it. And just take a look at this, and you, like I said, you already know how it works.
Well, if you called this auto fib, would that still be okay?
If you called this auto fib
instead of self?
Yes. Yeah, that would be fine, I think. Okay.
It's a different scope, but it's not.
It's
not there yet.
It would be fine, but yeah, it would be fine. I was about to say a little misleading, but I'm not sure. It depends. I don't know. What's your take on this? The trainers in the room. What would you recommend in this kind of situation?
I think it'd be kind of cool to actually call it fib and then see how the code reads later, because we haven't actually used this yet, right? But it sounds reasonable, and it should be allowed because it is definitely a different scope.
Yeah.
If it is allowed, it'd be like the one type of shadowing I'd be okay with.
Yeah, Robert said in the, would it trigger shadow warnings? I don't think so. I don't think, because you can't, fib on the outside isn't actually named until the lambda expression has been evaluated and bound.
It might trigger on GCC. GCC is a little trigger happy on its shadowing warnings.
Okay. Okay. So this is recursive Fibonacci. Of course, this is the example everyone uses, so I put it in. Side note: don't really implement Fibonacci this way. Implement it with the generic raising a matrix to the power. It'll work on it. You can find it in Elements of Programming. You can see it in a Sean Parent talk. It works with, it's a generic version. Anyway, now here's a slide which is new and a bit more exciting, and it's the interaction of overload sets. So overloaded is a thing here that inherits from a bunch of lambda expressions and has that variadic using statement to use all of their operator parens. I think, Jason, you've covered this in the C++ Weekly. Probably you've got in your series of 20 talks on lambdas. I'm sure this came up. And we're visiting the overload set, right? So a tree is a variant of a leaf. and a node pointer, and a node is a left tree and a right tree. Now, what's happening here? Well, we're visiting the overload set. So we've got two overloads, one to deal with whether it's a leaf and one to deal with whether it's something else, i.e. a node star. However, let's think about what type is deduced in the second lambda here. Well, it's not a node star, it's the overloaded, right? Because it's the most derived static type. So yeah, it's not a node star, obviously, because the node star is second, but what's deduced for the self type is not the lambda, I should have said, not the closure object that is the lambda, it's the overloaded that derives from it. And so we can call visit again on self, which is an overloaded thing. And it's this mutually recursive formulation. Everyone following what's happening here?
I'm just have a minor confusion as to how visit is visible from inside overloaded.
It's stood visit. I just didn't write the stood.
Oh, okay.
Yeah, it's a regular stood visit on the variant, on tree, like the last line. See, that's the variant. And so, yeah, when we visit tree with this overload set object, it's going to call one of these functions on that overload set object. And so that second lambda expression will deduce the type of self as the overload set object. And you know, you get this kind of very nice formulation of kind of mutual recursion. So that's awesome. Okay, my next slide looks like, yes, so sort of like what I said earlier, a non-capturing lambda, probably we can make it conventionally by value into its own, into it as the parameter of its own closure object. And then the compiler can completely optimize away the reference forming and the passing of the empty object. As Jason said earlier, that paper is 1169. The one that says the operator paren of a non-capturing lambda. I think it is only non-capturing lambdas, but it might be other lambdas. I think the paper as written might be starting off small to begin with. And for the longest time, I actually had the mental model that the operator paren of a non-capturing lambda was static, but it isn't. It isn't. It definitely is not in C++ today. All right, comments in the chat. This is something we really can't do today. Yes, this is something we cannot do today, for sure. And it's pretty cool. So there are a few caveats with lambdas, right? So here's a lambda expression. And if you go to CPP Insights, you will see something like this, right? And this is how we all think about lambdas, because this is what the compiler generates when you write this lambda, right? Everyone nods. The answer is no, right? The standard based answer is no. What you're seeing, this class _ lambda is a convenient way to think about it. But the truth about lambdas in the standard, about lambda expressions and the closure objects they produce, is a bit more complicated. The closure objects have no defined layout, no defined size or alignment, no defined member initialization order, in particular, not the order you capture things in. And in fact, no defined members. When you access members inside the closure, you aren't using variables, you're just using aliases that the compiler is allowed to do whatever with, right? And this is by design. This is so that sufficiently smart compilers can make optimizations. Jason said, but required to have operator paren. I'm going to say yes. I guess so. I haven't read. I've read. Jason, you're talking, but you're muted. It looks like you're talking, but you're muted.
I'm just moving my mouth over here. It's fine. I'm talking to myself. It's yes. I think it's required to have operator paren. I did mean to ask you that. Yeah.
Yeah, I think you're right. But it's not required to have any kind of layout or, you know, any number of members defined. So when we see this in CPP Insights, it's really just a representation. Now, odds are that your compiler today does implement exactly this that CPP Insights shows, but it's not required, and the standard is very pernickety about this. And the result is that, you know, some fairly interesting things for this proposal. When you use self in a Lambda expression, you can use decal type on it to find its type. You can call it, but you can't access member variables using self.member syntax because there are no member variables. Those are just aliases. And this syntax does not work by design. There's no such thing as self.x. But then again, there should never be any need to say that because you can just say x.
There is a need. Sorry,
go ahead.
There's something we can't do right now that like mutable captures. And that where I was going to ask is if we could have used that for that, but obviously we can't because so where you have because the operator paren is const by default, but if you put mutable, it's not const. Right. And when you start wrapping lambdas, like say in a callback system, you got to match that. Otherwise, you know, your const ones can't call the non-const ones. Or just use mutable all the way down. Right. But if we had with that, I was wondering if we could do a mutable capture where we could, you know, but I guess we can't. But okay.
I'm not sure what you mean by a mutable capture.
So say I capture by value.
Lambda expression is mutable.
So yeah, you know, if you make the lambda mutable, you can mutate a bival capture.
Right.
Okay. But what I'd like is to be able to mark a specific capture as mutable, and you know, so that we could keep that const on the lambda itself, so that you don't get when you start doing chains of them.
Marking a specific capture as mutable.
Yeah, I was hoping we could use this for that, but
no, that's I'm not aware of a proposal for that, and that would be a completely orthogonal proposal.
Yeah, it is. I was just wondering if we could work around it with this, but yeah, you just answered it.
Okay. So yes, okay. This slide sort of presents that caveat. You can do these two things, which already give you a lot of power. But when you're inside the closure object, just be aware it's not a regular object. It doesn't have a layout, etc., etc. Vaughan said, interesting that with this auto self, this is not equal to ampersand self. Right. the this tag on the first parameter is giving you the closure object. But when you say this inside the lambda, it's still referring to this capture, right? It's still referring to the object outside the lambda. That's important. Yeah, the meaning of this inside the lambda is unchanged. Okay. So let's have a look at a bit of miscellany here. A few remaining observations, including one that I actually realized was quite cool. So Chris at the top of the talk mentioned concepts. We can think about how concepts interact with this a bit, which I'll do in a couple of slides as it turns out. But this is another thing we can't do today. I haven't, you know, this is very early days for this proposal. It's not implemented any compilers yet. And so I haven't got a chance to use it in anger really, but I don't know. What do you do today if you want to constrain the value category of a closure object from a Lambda? I don't think you can. You have to do it in a struct like this. If for some reason you only want to be callable on L values and not R values, for instance, but you can totally do this with P0847. If you try and pass this an R value closure object, you're going to get the error that says you can't bind a mutable L value to an R value. Okay, so that's something you can do which someone might find useful. A bit more useful, as we said, so anywhere you can put a template, you can put a concept. That's true in general. Like this is an example of how this feature isn't magic. You can just combine it with other C++ features that you would expect. And you can, for example, do this to make your method safer. So now any of your derived classes that call this function need to be regular types, right? And so it's kind of like we can get a bit more control over what derived classes can do. We can constrain them appropriately, which we couldn't do before, really. So you remember the template method pattern from design patterns? This is where, you know, the base class has a template method and it calls virtual functions that are implemented by the derived classes. Maybe some of you remember this. With deducing this, now, as this is expressed in the book, and indeed in many code bases, it just looks pretty much like this. With deducing this, you get to constrain the template method, right? You get to make sure it's actually callable on your derived class. And you know, so there's no virtual methods here. The virtual methods have gone away, but what you're saying is I can use this template method now statically if my derived class implements the things I require in my concept. So we get kind of static template method. This is actually, when you strip what, I just had this realization the other day, it was like hitting myself over the head. This is exactly what CRTP is when you strip all the boilerplate away. It's the template method pattern. It's just so obfuscated right now. I didn't even recognize it. But, you know, CRTP is basically this, and kind of the obvious thing to do is to constrain the mix-in method here, or the template method. So the template method pattern is super useful. CRTP is super useful. And with P0847, we finally get all of these things. We finally get to express it simply in a statically optimized manner, where it's safely constrained, where it's appropriately encapsulated, and where it's generically usable. And I think up until now, we haven't been able to get all of these properties because, you know, as we saw, CRTP is not that simple. Virtual functions, they're not statically optimized unless you hope the compiler can devirtualize, but, you know, that's iffy. If you try and use free functions, they're not really best encapsulated. Like, you don't get to look up the data inside your object. If you use friend functions, you know, friend functions and free functions both have this problem with generic code in that, you know, they're not kind of uniform function call syntax callable. You can't call them like methods. So with P0847, we get to have our cake and eat it too. I have this slide in here because I wanted to explain a bit about some minutiae here. So as I said earlier, this is the old style and the new style, and they do the same thing. Like, they're both still valid and they do the same thing. So it will be an error to define them both. However, they are slightly different. And the difference is that really when we put that in, when we take that implicit object parameter and we make it explicit, we are a bit more like a free function. We're still a member function, but, you know, sort of cognitively, we're a bit more like a free function because we made that implicit parameter explicit. And so we had some choices about what to do, how to access, in particular, how to access member variables. And the choice that makes sense at the moment is to work like a free function. So sort of by accessing member variables on self like this, rather than the third one works, the first two do not, if you choose this formulation. Now, it's not a free function. You still have the access rights to S. Like you can access private members because you're still a member function. It's just the syntax you have to use to access member variables of S. Is that clear? Okay. Now, given this, it's possible to...
Sorry, I'm just going to interrupt.
Sorry, go ahead.
If I had a derived class,
Yeah.
The derived class had the private int I, then this would not compile.
I think the next slide covers that very case.
Thanks.
Yes. There are some pathological cases you can get into. So deduction to derived type, firstly, means sometimes you have to defend against shadowing, right? If you want to access bases I, this is the case where we're just shadowing, we're not yet private. Derived has declared an I that shadows bases I. So you can't just say self.I here, assuming you want the integer, because it will get the double in the case of calling it on derived. But you can use the regular base access syntax. These kind of badly behaved classes are ill-advised in general, come up relatively rarely, but this is exactly the kind of thing that standardization has to consider. And to go on to the example that you raised, here is the example. So a private inheritance, right? Or indeed making I private in derived, right? Because F is a member function of base, right? And so it has the access privileges of base. If things are private in derived, it has self is a derived or is a derived reference of some kind, but we're in a base member function, so we only have the access privileges of base. This is a little strange to think about. This is new kind of thing. So although you can access, you can sort of think of F as a member function of its. One way to think is a member function of the self, but it's not really that because of this kind of situation. And yes, Darryl points out that you could friend base. What would you have to do? Yeah, you could friend base inside derived. Yeah, I think that would work. But you know, friends don't let friends use friend, mostly. So yes, in F can access private members of base, including private static members, of course. And yes, yeah, right. So F gets, let me say this a bit more clearly. F is receiving a reference to derived. That through that reference, you can access public members of derived. You can access, and because you're inside F, which is a member class of base, you can access private static members of base. But because you have to access non-static members through the derived, you can't access members of base because of the private derivation. If the private derivation were not there, you could access protected and public members of base, right? But not private members of base because you're working through a derived, right? So, you know, these kind of things are kind of involved, but not that complicated if we just sort of apply the C++ rules that we know, but they are involved and the sort of thing comes up in standardization. Anyone have any questions?
You described it as a badly a badly designed set of classes, but really, I mean, as a base class author, you don't have control over all of the multitudes of derived classes that are going to be derived from you. I mean, they're in an infinite number, and it would like restrict you on changing base. Like if you wanted to introduce change the name of a variable, or add a variable, it seems like that would have the potential for just kind of randomly breaking lots of clients.
Yeah. So there's good news about this, and it comes from a surprising source, which is plain old C-style casts, which ignore access. You can totally C-style cast self to a reference to base here, and everything will work. I offer that. It's in the paper. It's a workaround for this situation. Like you know, this is C++, so it's possible. C-style casts are coming back. Trainers take note. Yes. I mean, hopefully this situation is rare for you to run into. Okay. Couple more things to tie up. What does a function pointer look like? And this, I think, is good news, because a function pointer to G acts like a free function, which makes it much, much easier to wrangle than member functions. I hate member function syntax. It's always problematic. And you can pass around pointers to member functions like free functions now with this style, because by making that implicit object parameter explicit, they're very much like a free function on the outside. So yeah, the type of PF here is a member function pointer, but the type of PG here is exactly like a free function would be.
I feel like as you keep going over this, it's helpful to just think of them as static functions, basically. I mean, they aren't, but but in many ways they are.
Sure. Okay. Okay. There are lots of ways to think about them. If that helps, fine. All right. So, ton of minutiae at the end, which may or may not be useful to know. The question arises to me, hey, ADT style, always deduce this. Why wouldn't we just do this now? So let me try to answer that. There are lots of advantages to doing this. As we've seen, you get massive code deduplication. You get correctness and completeness from the compiler. Your class interface gets sort of simpler and safer on the outside, as it were, because you can do things like constraining your descendants. You get simpler member function pointers. You get all this easier patterning with template methods and CRTP. And, you know, sometimes you're going to need to use this, so you might want to be consistent in using it. And in my opinion, it's very teachable because we already have this mental model of the first implicit parameter. And if your code is mostly compile time polymorphism and templates, then this is probably a pretty attractive option. However, it's worth mentioning the downsides. If you're not used to templates, there is a certain amount of implementation complexity. You know, you have to wrangle the value categories. We saw like T and forward like. And of course, there's always the compile time consideration. You know, takes longer to build templates usually. Also, sometimes, you know, the price of having the ability to deduce types is having to deal with the complete deduced type. Sometimes you just want to say, is this console mutable? But that's not how the compiler works. You get the whole enchilada, the value category and all, and you have to deal with that. So you kind of get over deduction from what you were hoping for. And finally, deduced template, deduced this methods can't be virtual, at least yet, right? So if your use case is going to involve true runtime polymorphism that you need to preserve, then, you know, that's your lot in life. So those are the drawbacks. And there's one thing that I'm sort of, I wonder whether it's good or bad. As I said, there's no, back a few slides ago, we chose to make implicit member access and access through this not a thing in deduce this methods, because you have the self, you access through the self. Is that good or bad? You know, it's a bit more to type in some cases. On the other hand, if you've written template code and you've run into dependent base types, oftentimes you have to put this arrow in front of your access. And that can kind of, I never quite know when to do that. The compiler sort of often tells me that I have an error, and I'm like, oh yes, that's right, I've got dependent base type, I need to type this arrow. That trips me up from time to time. So, you know, this is kind of good some, bad some. In the end, as I hope we've seen, this is a relatively small language addition, but it interacts well with the rest of the language rules. I think it will make lots of code easier, certainly a lot less code in libraries. And we get some new possible patterns. And you know, at the time now, I don't know what they all are. These are some of the ones we've thought of. By value, object parameters particularly, you know, we've thought of that a little bit, but that might turn out to be a lot more powerful. CRTP gets way easier. Mix-ins get way easier. Recursive lambdas, which, you know, we've wanted since we had lambdas, they get really easy. And we get to mix in concepts and constrain member functions appropriately, and constrain, you know, member functions through our derived types, I guess. The bottom line is that you apply the rules you already know, and most likely it works as you expect. Thanks for all your questions. Thanks for listening. That's my talk. Thank you.
Thank you, Ben. I don't know if you want to take any other questions before I stop recording. I do have some questions, thoughts after we stop recording. Personally, I want to go them after we stop recording because I have the power to do that. Doesn't matter. I can edit myself out regardless.
By my clock, that was a little too long for CppCon, so it's good. It's good that I got the chance to do this. Should this be accepted, it will fit into an hour.
Yeah. All right, I'll go ahead and hit stop recording because no one else is chiming in here. Oh, here we go. There's one other question.
It feels like ADT, as I've dubbed it, always deducing this, would open up a lot of inadvertent customization points in a base class that are controlled less. I'm not sure what you're thinking. It's not controlled less as a base author. Assuming you're doing the template method pattern, you are providing that customization point, I guess, is the observation. So if you're doing template methods or CRTP, it makes sense to constrain those functions with concepts. And that's a sort of, I guess, a side point from what deducing this offers, but I would strongly recommend that anyway. Chris says, can you talk about the deducing the return type with like t a bit more? In your example, it returned like t ref, but why the ref? That was early in the talk, I think, in the getter. Let me go back here somewhere. If I can find it. Somewhere around here, right? Yeah. The idea with this getter is The ref is on the end for the same reason that the ref is on the parameter. I think it's the reference collapsing rules, right? So like T will produce either an L value reference or an R value reference, and that will collapse either to an L value reference or an R value reference. Because when you have, the idea of this getter is that it's kind of a perfectly forwarding getter. When you have an R value S and you want to call get on it, what you want is an R value string. In other words, you want, or I should say, if S is an L value, you want the L value to the string. If S is an R value, you want the string to get moved out. And so the ref on the end, I think, is just how C++ works given the reference collapsing rules. Jason's nodding. I think maybe this is something you cover in your classes, Jason?
No, I explicitly avoid talking about reference collapsing rules actually, but it's how standard forward is implemented and how standard move is implemented. Actually, they both rely on reference collapsing rules.
Right. So
it seems reasonable to me that that's what you would need to do a similar thing here.
Vaughn said, if you have this auto self, do you still have a this pointer? I
don't think you can. This is where I said it's
to reference this inside explicit object parameter member functions.
This is why I think it makes sense to think of it at, like, I think from a compiler perspective, they are static functions, which is why the reference function syntax or the function pointer syntax is free function, because it's the same thing as a static function.
What do we have? Okay, so this is a lambda, so it's not a very good example. This is a lambda as well. Where did I have by value callable? By value this. Okay. So in sorted by here, you are not allowed to say this. So the question of do you have a this pointer is really no, you don't. You have self. You have all the access rights to self that you have by virtue of being a member function, but it's as if you're a static function, I guess, as Jason says.
It's a static function with syntax sugar when you call it.
So that brings up, did you ever consider making it that to say static?
It's not a static function. It's a member function, and you have to call it on a member. That's what it is. So making it a static function is tantamount to making it a free function where you have to pass in the thing. And so it has all of the...
But it is a free function. You have to pass it in the thing. It's just the compiler does it for you in some cases.
Well, sure. All right. But you can call sorted by from within another member function, right, as well. It acts like a member function.
Right.
You had an example on one of the slides of different ways to call. It was after this. It was maybe in the lifetime management. I don't remember.
Let me just go through here. Different ways to call this one.
There was one with where you called it using member syntax. Yeah, that one. This one.
Mm-hmm.
I think I see what happened. Okay, I had a question about that, but on second look, I understand it now. Never mind.
Right. So the PG call, second from the bottom here, it's a function pointer. It's a regular function pointer. Yes. So it does act like a free function.
It acts like a static function on a class is what it acts like there.
Right.
I'm sorry, I'm going to keep coming back to that because that's totally what it's exactly the same thing that would happen if you got a pointer to a static function, like literally exactly the same thing that would happen.
Well, yes, but inside of G, you can call f.
Via the explicit pointer that you're given
Yeah.
to it. It's still not an implicit call to any of the members. You're still having to say access this thing via this pointer.
But you can call, but at that point you can call s.f inside of G.
Right. Yes. I'm saying though, but everything else about this that's happening here is exactly like a static function. And even inside the function, it's exactly like a static function. If I wrote a static function that explicitly took a reference to my outer type, it would behave almost exactly the same way in every way, except for the compiler wouldn't know to automatically pass in a pointer to this when I tried to call it. The access levels would all be the same. Getting a pointer to the static function would be the same.
What's the paper that makes free functions callable like members with dot syntax?
I don't know the
Form
number.
call syntax.
That's never going to happen. Yeah.
But it feels similar to your view of this static function that you don't have to pass in the object as a first parameter.
Yeah. So that is important in generic code, right? That's the big draw of uniform function call syntax as well. And this is like opt-in uniform function call syntax, right? So in generic code, you can just say object dot method. You don't need to know to say method of object. That's a pretty big deal for generic code.